In this video, we'll look at an example of running a restricted Boltzmann machine learning algorithm with contrastive divergence on some given data set. And in particular, what we'll look at is what types of features, so what types of hidden units would a restricted Boltzmann machine learn on a data set of handwritten characters, handwritten digits. So here are a few here's a visualization of a few training examples from a data set called the MNIST data set. It's a very popular data set for neural network research. So in this case, the images are 28 by 28 pixel images. And what we can do is use these images and put them into the form of a vector and then just train the restricted Boltzmann machine on these examples, and then once that's done, look at the types of features that each of the different hidden units represent. To do this, what we can do is we can take each hidden unit and visualize the connections between that hidden unit and each element in the input vectors. I'm actually drawing arrows. Though remember, the restricted Boltzmann machine is undirected, but what I want to emphasize is that each of the illustration here actually corresponds to the vector of connections between one hidden unit hj and each of the pixels x1 up to xd. And because x is actually an image, I can take that vector of connections and actually reshape it into an image in order to visualize it. So specifically, each square here corresponds to one hidden unit, and then the color of the pixel, the intensity of the pixel, says something about what's the value of the connection between that hidden unit and the pixel at the same position in the original image. So gray, in particular, in this visualization, corresponds to a weight equal to 0, whereas a white pixel corresponds to a weight that is positive, and the wider it is, the more positive it is, whereas black corresponds to negative pixels, and again, the darker the pixel is, the more negative the weight is. And so what this means is that, for instance, if we take that hidden unit, when we compute the probability of that hidden unit being equal to 1, it means that we're doing a essentially applying what we can think of as a filter on the image. So we're multiplying this set of connections to the image, and then we're summing the product of each element here in this connection with the image. So if part of the image is gray, it means that we're multiplying by 0. So whatever the value of the pixel is, it won't actually have an impact on the value of the probability of the hidden unit. If it's white, it means that if the pixel is non-zero, then it will actually increase the probability of that hidden unit. So if we add white pixels here in the original image, then that would increase the probability of that hidden unit to be equal to 1. And if it's black, like here, it means that, on the other hand, if the value of the pixel is positive, there is non-zero, then this will actually decrease the probability of the hidden unit being equal to 1. So an interpretation of this particular neuron is that it detects whether there's a pen stroke with this orientation where there's background here, and we actually have a stroke like this. Similarly here, this hidden unit would be sensitive if there's a pen stroke like that in the image with some background here and here. And so we actually find that a lot of these hidden units have essentially learned that in characters, handwritten characters of images, there are essentially pen strokes. So, this would be another pen stroke here, where we have a pen stroke kind of like this. We have other units that are not necessarily as easily interpretable as pen strokes, but still it's learned some a decomposition essentially of what a handwritten character is as a set of different pen strokes in different isolated regions of the image. And we can think that it's not too hard to convince ourselves that these types of features might actually be useful in order to identify, for instance, what's the category of the image. In particular, when we have an image of a character, it's much more easier for us to describe it as a composition of pen strokes than as a composition of pixels. So perhaps a representation of an image of a character as a set of pen strokes might actually make the identity of the character much more evident to the learning algorithm. Unfortunately, RBMs are not very easy to debug, so we can actually use a finite difference approximation of the gradient and compare that with our estimate of the gradient in the learning update. And that's again because we have a partition function which is intractable. So I just want to mention a few tricks that people sometimes use to try to debug their implementation. Sometimes people look at something we'll call an average stochastic reconstruction, which is just the squared norm of the difference between each training example and the result of performing one step of Gibbs sampling starting at xt. And so normally you'd sort of expect that initially you'd get a high value of that average, and then this would sort of get smaller and smaller and smaller. We don't necessarily expect this to converge to 0, for instance, but it should, in general, we sort of expect it to decrease. Also, we can visualize the features that are learned like we just did. If we have images, then we tend to expect things that are visually meaningful, like edges or pen strokes for handwritten characters. And another thing we can do is actually try to approximate the partition function in order to be able to evaluate what is log of p of xt. And then if we can do this, then we could, for instance, track on the training set how this progresses. So in particular, the average negative log likelihood, we'd expect it to decrease on the training set. Now, getting a good approximate of this is not very easy. There is some work that I'm citing here, which has suggested a fairly efficient way of estimating the partition function. Still, it's efficient for a fixed RBM, but it will still require not an exponential amount of time, but still a meaningful amount of time for a fixed RBM to compute this. If we wanted to actually track how the partition function changes as we're updating, reperforming that computation can be still expensive, though there is some research for trying to track the partition function, which you can find online. But essentially, we have tricks for trying to get an idea as to whether an implementation of an RBM training works well, but these are really tricks, and unfortunately, we don't have a tool as reliable as finite difference approximation.